It's really an honor and a pleasure to speak to fellow GRASPees, and thank you so much for the opportunity. I have to say that when Chris invited me to talk in this forum, I was having a bit of a hard time picking a topic out of all these things I've recently worked on, because any of these stories have elements that would resonate with this audience. I ended up resisting the temptation to talk about some of the more recent developments, which I'm also excited about and keep thinking daily, and settle on a story that is rich, mature, and somehow, I'd say almost complete now. And this is the one on networked radiation detection. So here, the problem is how to coordinate a swarm of drones, or any type of autonomous vehicle for that matter, that carry commercial off-the-shelf inexpensive radiation sensors so that they can detect the presence of weakly radioactive material on a mobile platform. And that platform can be a ship that enters port, it could be a container truck passing through a border crossing, it could be a van cruising down a New York street. The trick here is to complete the detection fast and without disrupting the flow of traffic. So no stop and frisk in that sense. So this project involved a number of people with different expertise. Besides me in platform and cooperative control, we have Poulakakis here in network decision-making. Huang has been assisting and leading the state estimation part. Chetan Bakhlajani was the expert in information theory and statistics. And Climeco and Carver from Los Alamos were advising on nuclear detection. And there was a host of graduate students obviously pulling the strings and doing the actual work on the ground. At a very high level, the problem is as follows. You have an array of sensors, which are basically just counters. They just register hits that come from radiation. They're numbered 1 through K. And you have a mobile source up here, which is emitting radioactivity with some specific known type. So we know the source emission intensity. I have white arrows and blue arrows to mark gamma rays that hit the sensors. And with blue arrows, I denote those that come from the source. And with the white arrows, these are the rays that come from naturally occurring background radiation. Now, inexpensive radiation counters have no way of differentiating between background and source rays. Now, the sensors supposedly have a way of computing, doing some local computation, and they report a statistic based on the cumulative ray count over a certain period of time to a fusion center over here, which is tasked to make a decision as to whether what has passed is radioactive or not. So now what we're called to do is to find strategies to move these sensors around relative to the moving target in order to maximize the probability of detection, subject to an upper bound on the probability of false alarm. And we want to do that without reliance on GPS, because we want to deploy the system indoors and in GPS-denied environments, and be able to work with very small radioactivity levels that would otherwise blend easily into the naturally occurring background. And also do it in a fixed time interval, because we know that this is so much time that we have before selecting appropriate action in the case that something is detected. Now, a little bit of background now. There has been significant work on network detection in the information theory community. And roughly speaking, this can be categorized into approaches that are based on first Bayesian inference, that is, generally speaking, computationally intensive and relatively slow, but gives a lot of information. Sequential probability ratio tests, here that do not have a fixed decision time that as we want in our problem. And Niemann-Pearson likelihood ratio tests, like the one that we're going to use, but the ones that exist out there are for homogeneous sensor nets and for static sensor networks. On dynamic mobile sensor coordination in confined environments, there's also a little bit of work, some using sample-based approaches with known limitations in dynamic environments, and others that also struggle to address cases of moving obstacles. And lastly, on distributed state estimation and target tracking, we have approaches applicable to two-dimensional workspaces only, others that explicitly utilize multi-state constrained Kalman filters like we do, but without target tracking, and some that might not provide guarantees on estimation consistency. So our thesis here is that by co-design state estimation, network deployment, and decision-making, with the final goal being to increase the accuracy of detection, we can not only improve the state of the art in each component technology, but we can also achieve detection times much smaller than what has been reported so far. So this is the algorithmic architecture that we adopt here. There are three main components. We have sensor control here. We have state estimation, and we have decision-making. And the three components are naturally coupled to each other, and they communicate with the output of one feeding and helping the function of the other. So our sensor platform of choice is an aerial vehicle, a relatively generic quadcopter. In this case, what you see is a very early prototype that we used. It's essentially based on the Pelican structure and fitted with commercial off-the-shelf components. So we have here a stereo camera and a visual inertial navigation system. It carries a small, lightweight radiation measurement payload. And the general idea is to keep the cost of such a unit low so that we can deploy them at scale. I won't say too much on the state estimation component of this work because this is not one that I was driving. But I will only note that this estimation filter updates two state vectors. One contains the position, velocity, and orientation of the vehicle, and has the biases of the IMU. And another state vector is for the target, and it's tracking derivatives of positions of a certain order. So all this information is fused and updated in a computationally lightweight multi-state constrained Kalman filter. And for the updates, the filter assumes constant acceleration on behalf of the target to facilitate estimation. Now, as far as the vehicle goes, we utilize, to control its motion, we utilize a differential geometric attitude controller, assuming thrust and moment as control inputs. And we use a reference spatial velocity to determine thrust, and a reference orientation trajectory to determine turning moment. And the last component is decision-making. And here what we do is we formulate a binary hypothesis statistical test, where the zero hypothesis is that the target, the moving target in the environment, is benign, doesn't carry any radioactive source. The sensors here 1 through K compute a particular quantity that we derived, and it's based on the Poisson statistics of nuclear emissions. And this quantity involves the perceived source intensity incident to the sensor, to each sensor, that depends on the actual source intensity, A, and sensor characteristics, chi. And I want you to notice that we have in the denominator the square of the relative distance between sensor I and the source or target T. So basically, the further away the sensor is from the source, the weakest the source appears to the sensor, and the more difficult it is to detect it. There's an inverse square law dependency that makes remote radiation detection particularly challenging. And we also, in this expression, we have a ratio of this perceived intensity over the known background radiation radioactivity rate, the naturally occurring radiation. So each time a count is registered by a sensor, this quantity is updated. And at the end of the observation time window of length tau, big T, the number is reported to the fusion center down here. And what the fusion center does is it multiplies all these quantities that it receives from the sensor and compares this product to a fixed carefully selected threshold. Now, there's an involved analytical and computational process that goes into the determination of this threshold, and which I'm not going to bore you with, but only tell you that this threshold takes into account how the source has moved relative to the sensors, and is calculated at the end just before decision is due. So if this product, which is known as the likelihood ratio, L sub t, is larger than the fixed threshold, then we conclude that the target is radioactive. So we reject the nominal hypothesis. And this is basically the Neyman-Pearson binary hypothesis test, which is the optimal way of distinguishing between two hypotheses, in the sense that it maximizes the probability of detection while accepting a certain predetermined small risk for a false alarm. Now, I want to stress a little more the importance of the inverse square law and give you a little bit of insight as to why this law is enforced here without doing any derivations, but rather demonstrate with this little cartoon why the square appears and why is the inverse relationship is in place. So this cartoon attempts to convince you that the percentage of rays that are coming out of the source and hit the sensor up here is proportional to the solid angle corresponding to this particular area. And the solid angle itself squares with the square of the distance between sensor and source. So the closer the sensor is to the source, the more likely it is to capture a ray being emitted from the source. So remember that our goal is to move the sensor around so that we can boost detection efficiency. So how do we do that? Here we understand detection efficiency as, in terms of time, being able to make a decision within short time intervals. What does short mean? We mean a couple of minutes as opposed to hours of observation. So the Neyman-Pearson test gives us a handle on how to proceed here. Once we compute analytical Chernoff bounds on the probability of misdetection and false alarm. Now, the actual probabilities of misdetection and false alarm are impossible to compute analytically, which is why we resort to these analytical bounds on them and use them as surrogates in the whole process. These analytical bounds involve the background rate here, beta, and also a constant tuning parameter that has to be selected before the test is conducted, and the quantity mu that I was showing you before that involves the perceived source intensity and which contains the relative distance between sensor and source. Now, the latter, this relative distance, is what we will grab to start unraveling this into a motion control strategy. And this is going to be done through the solution of a nonlinear optimal control problem. Now, this nonlinear optimal control problem aims to minimize this Chernoff bound on the probability of misdetection. And surprisingly, without throwing in platform dynamics and constraints in this problem, it turns out that it actually has an analytic solution. And this analytical solution gives us insights as to what the optimal motion strategy will be. Now, not surprisingly, this optimal for detection motion control strategies call for the sensor to close the distance to the target as soon as possible. So with this key insight as to what the sensors should do with regards to the moving target, we take this insight from the optimal control formulation and we try to realize it in the context of all the other constraints that are imposed. So a motion planner here for these sensors needs to help them intercept their target as soon as possible, be compatible with vehicle dynamics to ensure feasibility of motion, and keep them away from obstacles. Now, the fastest interception objective here is implemented via a steepest descent approach based on potential fields. Navigation functions specifically, and I'm going to show you what I mean. But here on the left, you see a little cartoon with the end result of this motion planning scheme, where a blue robot chases a red target in a constrained environment. And maybe we can notice how the robot cuts the corners to gain an advantage of its target and eventually intercept it. So we can guarantee these specifications in this theoretical framework of navigation functions using a new type of time-varying navigation function. The navigation function is time varying because the destination contains the target coordinates here and it changes over time. And it's not the destination itself is not a single point as in the traditional formulation, but it's a whole manifold. It's essentially a safety bubble around the target because we don't want our sensors to crash onto the target once they've intercepted. So we can formally show that this construction here has navigation function properties. It's free of local minima, despite the dynamic nature of the goal configuration. But exactly how to do this can be a subject of a whole other talk, so I hope you'll allow me to skip the details. And just trust me when I tell you that this works as a navigation function in this dynamic environment. So here's how this would work and how it would look in a gazebo simulation scenario. This white spot here is our sensor, and the black ground robot is the target. So the navigation function gradient informs the geometric controller on the vehicle and moves it to intercept the target while running its onboard filter for localization and target tracking. And these are some of the features in the scene the sensor perceives. But I also want to show you very briefly how the world looks like to the robot through the eyes of the time-varying navigation function that has as its destination the moving target. And here on the left is a snapshot of the navigation function that was used in the scenario that I just showed you in the previous clip. And here on the right is another different example that shows how the workspace, the navigation function changes and evolves over time as the target moves about. So in this slide, I have some performance reports on estimation and target tracking for the scenario that I showed you before. And without saying too much here, it's worth mentioning that the motion strategy itself seems to be split into 3 stages: the takeoff, interception stage, and disengagement once the detection is completed. And naturally, the smallest the safety bubble is defined around the target and is allowed to be, the easier and the faster it's going to be for the robot to detect the source. Now, moving on now, we wanted to extend this methodology for cases where the environment is not fully known and incorporate elements of reactive navigation, where obstacles could be detected and avoided on the fly. And towards this end, we integrated a real sense camera on the vehicle to obtain short-range point clouds that we could use for collision avoidance, local collision avoidance. These point clouds, especially from a real sense camera, are only 2 to 3 meters in length in front of the vehicle, which places limitations also to how fast we can fly the vehicle and expect robust collision avoidance. So we want to integrate deliberative motion planning through navigation functions with reactive motion planning, and we can do that through receding horizon control. The navigation function provides a reference waypoint for the reactive motion planner to hit using a dynamically compatible trajectory. And this trajectory is constructed based on information from the point cloud. So the reactive motion planner considers different rays to points at the end of the point cloud, ignores the ones that are intersecting with obstacles, and weighs the remaining ones according to how close they come to obstacles for safety reasons and how close they reach the designated intermediate point or waypoint, and that weighs performance. So there's a weighted sum of these 2 objectives that determines what the optimal ray is. And given that optimal ray or direction of motion, if you prefer, and the vehicle dynamics, we use a minimum snap reference trajectory, which can be computed through this optimization problem that actually has closed form solutions. And we trace this trajectory in a receding horizon fashion, in the sense that in every update cycle of the planner, a new point cloud is collected, new rays tested, and a new trajectory is constructed and followed for a small period of time. And this small clip here illustrates how this reactive controller works. Here we don't have really any maps for deliberative motion planning. And this squad here is going to try to avoid the trees that are directly in its flight path. The speeds are relatively small here, but I want to emphasize that there's no GPS data that is used. And this fact is actually demonstrated a little better in the indoor version that you're going to see in a few seconds. And I also have another video where we push the limits of how fast this thing can go with reactive navigation. So this is the indoor environment testing, again, with reactive collision avoidance. Once again, there's no map that is used. The objects are detected on the fly and are being avoided. The clip, I think, continues on with some more gazebo simulations, which shows interactive, reactive target interception and tracking. So here we do have the tracking, the target in the picture as well. But I want to jump and show you another case where we actually combine target interception and tracking with radiation detection. So the target in this case is a ground robot. You're going to see it right there. It is in this green box. It carries a radioactive source, which is enclosed in this little white box in here, and it moves inside this abandoned industrial warehouse that we have on campus. The robot detects its target using a mobile neural network, comes close to it while keeping it in the field of view of its camera, and stays close to it for just enough time to determine confidently if the box, the white box here, contains the radioactive material or of the anticipated intensity. And the white cone shown here is basically the short-range point cloud provided by the RealSense camera. Now, at the end of the day, this is how the detection would look like. In this graph, in purple, you have the relative distance between robot and target that fluctuates with tracking. The key variable here is the ratio, this red line, the ratio between the likelihood ratio and the threshold. And when it crosses zero, this means that the detection is confirmed here. In this case, for this extremely weak source, we can handle it by hand, but we're told that we're not supposed to swallow it. Detection occurs in about 90 seconds. Oh, and this is the clip that I promised with faster reactive navigation. We have trees and foliage, and we start relatively slow at 2 meters per second. And I think you're going to see Intrajit in a little while holding the remote. There he is. Not that he will be able to save it if it went for a crash, but anyway. So this is the flight with 2 meters per second speed. It goes on and it lands. It's a very short test. But here's the interesting part where we pump it up to 4.5 meters per second. There's a more aggressive maneuvering in this constrained environment. Takeoff. It's kind of scary when you see it in a first-person view. It's a close call, but successful avoidance. And right about here, it starts to land. This is a portion where we test the dynamic obstacle avoidance, moving obstacles. Again, in an outdoor environment. And here we have both reactive obstacle avoidance and target tracking. Relatively small speeds at 2 meters per second. The next clip is going to show an indoor version of this. Indoors, we didn't have that many interfering obstacles. The obstacles were more on the side of the warehouse. That's the warehouse you were seeing before. Again, target tracking. The video is sped up a little bit to gain time. And I think this little clip ends with an outdoor experiment, same story, target tracking, just outside the warehouse in an more open environment. But maybe we can skip that for now. Okay, so now I want to show you how this performance can be boosted in a network scenario where sensors can share information between one another. So what you see here is the original setup. And this is the same setup again, only drawn slightly differently to hint at the fact that the sensors are moving around the source. So what we're going to do here is change this paradigm where everybody reports to a fusion center to another one where there's a directed communication graph between the sensors, and sensors exchange information based on what they have seen. And basically, any one of these sensors can play the role of a fusion center and decide for the whole network. So in this decentralized decision-making scenario with K sensors, the question that comes up is, who is best to decide? Who is the best decision maker? And the answer comes down to basically to the quality and quantity of information that each sensor possesses after this information has been propagated through the network. The quantity is dependent on how the sensor is configured and located in the network, basically how central it is in the graph and how much information flows through it. And the quality of information is determined mainly by how close to the source the sensor recording the data was when the source was passing by. Now, if we assume that the sensors transmit the likelihood ratios to the direct neighbors over one clock cycle, and we could have multiple clock cycles, then we can imagine that the sensing information propagates to the network after K hops, and we can contemplate K independent Niemann-Pearson tests, one for each sensor. And here it turns out that the notion of closeness centrality in networks can help us identify the best decision maker. Indeed, the node with the highest centrality, closeness centrality here, has the highest potential making the best decision maker for the whole network. And as I indicated, it's basically a game between quantity and quality of information. And we're going to get a deeper look in this in this slide. I want you to notice this this network, essentially multiple or stacked Niemann-Pearson test. And notice that the threshold quantities lambda prime here on the very right, in fact, express the decision-making accuracy for each sensor. Because the lower this threshold is for each sensor, the more well-informed the sensor turns out to be after data propagation. So they are in better place to make a decision for the whole group. So we can see these lambda primes are essentially expressed as a product of a term that is dependent on network topology and communication, this one here, involving the adjacency matrix of the whole graph, of the communication graph, and a term that captures the quality of each sensor's data content, and the latter depends critically on how close the sensor was during the source journey through the network, and it involves this ratio mu that we have seen before, and the background that is local to each sensor. So this is the interplay between quantity of information and quality of information that determines the decision-making capacity. Now, we have benchmarked this type of performance increase using government data sets on radiation measurements, and found that we could have an order of magnitude in time savings for detection compared to a Bayesian approach that had been originally used for this data set. In the graphs in the bottom, one can see that the most central node in this network is essentially identified as number 8. And even if in isolation, it would not be able to make the fastest decision out of all of them, in the sense it would need more observation time to acquire enough information. After the information propagates through this minimum spanning tree, it will only take him like 3 seconds to make the decision for the whole network. And if you're wondering why in this case it took 3 seconds as opposed to the 90 seconds that I needed for my quad earlier, it's because the source that they have used in this government data set is hundreds of times stronger than the one that we have used in the warehouse I wouldn't go anywhere near that source that went through the static sensor network in this case. Now, when you deploy multiple sensors and you collect data from all of them, another question that comes up is how exactly you need to deploy them and keep them moving around the target. And to that end, we looked at where the optimal what are the optimal sensor platform formations while tracking a mobile source. By formalizing a discrete time constraint optimization problem, where we minimize the collective probability of misdetection, subject to an upper bound on the probability of false alarm, and including in the measurement statistic that we have been using before, the mu, and constraints on how close to each other we allow the sensors to get and how close they can be to the source, to the target. And what we found surprised us a little, because instead of finding all sensors tightly grouped and evenly distributed around the target, kind of like this, the optimal formation for decision-making actually places one of the sensors as close as possible to the source, to the target, and then as if placing one sensor at a time and building the formation progressively, it places the others as close as possible to the source, given the constraints, but not in a way that interferes with how the first sensor was placed before. And the idea behind this solution seems to be that the key to get the best decision is to place as tightly as close as possible at least one sensor, make that the decision maker, and use the rest to provide some supplementary but perhaps non-critical additional information for the group. So this little clip, and I'm not sure if we're going to play it all, shows sensor coordination with optimal formation, at least in simulation. And here we have formations of different sizes, tracking the target in a cluttered environment. And what happens is that they first fall into formation around the target, and then they follow it around while keeping a formation and avoiding obstacles along the way. Different sizes of formations, multiple vehicles, different densities in the environment. Okay, I'm not going to stay here for too long. Performance improvement. So we can actually measure the performance improvement due to the optimal formations that basically tells us to put one sensor as close as possible rather than evenly distributing the distance. And here in the blue curve represents the bound on the probability of misdetection for the uniform distribution. And the others, the yellow and the blue, is for the optimal formation, with the only difference between the two being that the yellow one is the absolute optimal, painfully calculated through a nonlinear optimization process, and the light blue one is the one that uses a very computationally expedient convex relaxation to the problem. And these bounds were computed using our radiation sensor, our measured background rates, and the activity of the source that we had available at the time. Things get a little more interesting, I should say, if not all sensors are the same, and some sensors are more sensitive than others. Now, the optimization formulation that I showed you before can take into account this type of sensor heterogeneity. And in this case, in the light of what we have seen in formation optimization, the result should not be that surprising. Here, the solution tells you that you should put your best sensor in the position of the designated decision maker and position it as close to the moving target as possible. So in general, what is new, possibly noteworthy and cool about this system, is the integration and co-design between decision-making, state estimation, and sensor control. That can be combined using, while preserving the theoretically established desirable properties. Optimal network decision-making that is decentralized and robust in the sense that any of the sensors can fail and another one can take the place of the group decision maker. You don't have to have a designated and fixed fusion center decision maker. We have fully autonomous radiation sensor deployment in a constrained GPS denied environment. The implementation is possible with basically off-the-shelf components, and low cost allows the system this this network, this swarm to scale up in size. And we can still achieve an order of magnitude improvement in terms of performance being measured by detection time, especially in the low radiation count regime where other methods might struggle to provide the solution. And basically to wrap up with some key take-home messages from this story, and without repeating the points of the previous slide, I would close by saying that nuclear detection and non-proliferation efforts are definitely facilitated by ongoing work in the material science community for better materials and sensors, but also by new and smart sensor deployment, coordination, and sensor fusion strategies. And this is where we, as robotics experts and engineers, can offer and contribute to this, to the solution of this grand challenge. So with that, I will close, take your questions, and thank you for your attention. Chris, questions from the audience?
Question.
Okay. I was just wondering, like, if you could explain more the intuition behind that optimal solution, like, why does one sensor have to be closest and be the decision maker?
Okay, I think I heard the question, but I would appreciate if Chris repeats it because it was from a distance and I.
So the question was, can you explain more on the intuition behind the optimal solution with one agent being closer?
Yep.
And being the decision?
Yep, that's a good one, and it goes back to what I was trying to describe early on about the inverse square law and the importance of that in the context of radiation detection. So basically what happens is that you may gain some in terms of distance, but you're losing more. I mean, the benefits that you get from having more sensors close rather than having one right on top are not so easily balanced. Basically, by placing one of the sensors as close as possible to the source, what you achieve is that you receive enough high quality information in a short period of time to be able to make a confident decision. Basically, the lower limit on when we can make a confident decision is determined by our bound on the probability of false alarm. So basically what we do is we collect data over a period of time and we watch the statistic, that likelihood ratio, that red curve that let me see if I can find it, that picture, and bring it up. There it is. Okay. So basically this ratio, this quantity here, this statistic.
I don't think your screen changed.
I'm sorry?
I don't think the screen changed.
Oh, I'm not sharing anymore?
Oh, you're sharing, but it's still on the recap slide.
Oh, I don't know why this. Okay, let me stop and try again. All right. So hopefully now the graph shows.
Yes.
Okay. So we need to keep a watch on this quantity, this red curve here. One thing that I didn't mention before is the dotted curves above, the green one and the blue one. So the blue one is key. This is the bound on the probability of false alarm. And you see the false alarm probability being at 1 for a long time, meaning that whatever you decide up to this point, it's not going to be confident. You have a very high risk of calling a false alarm beyond the probability that you have acceptable, the bound that you have acceptable. And after a certain point, as information has accumulated, this bound drops rapidly. And this starts to define a regime where you can start thinking about making a decision. It's not ready yet, but it's getting close. So unless you place your sensor really close to the source, this curve is not going to drop down quickly. So you can still use an evenly distributed formation around your source, but it's just going to take you longer to be able to make a confident decision. And it's precisely because if I hopefully okay. Sorry. Precisely because of this inverse square law relationship here between relative distance of sensor and source. This is what gets into the optimization problem and gives this type of solution. So this weighs very heavily on the outcome of the optimization.
Thank you. Could you speak more on the co-design between the three components, the main three?
Mm-hmm. Yeah. Let me stop and redirect to the slide that I have in mind here. I know I didn't stay too long here on this one. Okay. So state estimation is a key component. It gives us estimates about where the robots are, where the target is, the environment. So the estimates that we get for states for robots and target work with motion control. This is straightforward. And so motion control and sensor deployment depends on the estimates, the current estimates about the target and the robot's locations. Now, what we do here, and this is where the co-design takes place. This explains to some degree the arrow that I had, the yellow arrow going from sensor motion to estimation. There is a component here that wasn't explicitly shown that we try. There's a multi-objective optimization under the hood that basically works by modifying the collective, the sensor motion so that it helps in the estimation, in the sense that it helps them maintain the features that they have picked and obtain new features from their environment. So in some sense, sensor motion also serves state estimation. So this is a two-way street. Similarly here, sensor motion, and this is the part that I emphasized primarily on this talk. Sensor motion helps network decision-making by regulating the relative distance between sensor and source, basically dropping the bounds on the probability. Now, how network decision-making, how radiation detection informs sensor motion, because the objective of the sensor motion strategy comes from the optimal control formulation that was based on nuclear detection, based on the Chernoff bounds as objectives in this objective functions in this optimal control problem. So there's definitely the coupling here where network decision-making analysis informs how sensor motion should be conducted, and sensor motion serves the purposes of decision-making. Now, state estimation also helps, or at least supports decision-making, because it gives the estimates in order for these local relative distances to be computed. But right now, we don't have the arrow on the other side from network decision-making to local estimation. So there's definitely some synergy between these components, which unless you developed all of them at the same time, you wouldn't be able to exploit. That makes sense.
Yeah, definitely. And then did you mention that you somehow, did you like a multi optimization scheme to figure out which one?
Yeah. Yeah, so there was a weighted sum in the that yeah the way that I present the story, it's it's kind of obscure where this resides. But it's essentially, we didn't showcase it that much. But basically, that multi-objective optimization that I was referring to, and it had to do with optimization or estimation features and motion control, was not exploited that much. At least it was not described in this version of the talk that I'm giving you today.
Yeah, no problem. I just thought it was interesting because like you would have to quantify like the ability for your estimator to do, and then like.
Yeah, I'll give you, however, one little insight based on the outputs, the outcome of this multi-objective optimization. At some point, it weighed heavily on our attempt and desire to have a lightweight filter on board of the sensor platforms. But when we increased the computational capacity on the drones, we're able to fully take advantage of that. Even if the multi-objective optimizer was running, we weren't able to see that huge of a difference in terms of the motion of the sensors. Essentially, what this was doing is, and maybe it was happening naturally, but basically the optimizer on the part of the local estimation was trying to avoid some of the singular trajectories on the part of the robots. And what I mean by singular is that there are some unobservable directions of motion when you're running the multi-state constrained Kalman filter. So for example, pure translation doesn't give you enough information about the attitude for running the Kalman filter. So there's certain directions of motion, certain trajectories that are undesirable from an estimation point of view. And these were the ones that were discouraged when we're producing reference trajectories for our drones. It turned out that by nature, or by luck, if you like, these reference trajectories that were coming out of our reactive navigation, this receding horizon scheme, were not singular from an estimation point of view. So we rarely had to modify the motion trajectory just to satisfy the needs of the state estimator. But the module was there. The module was there and running.
Makes sense.
Yeah, so I have a question about the application, and it's more because of my lack of knowledge in the area. So there is the inverse square law for the intensity of the radiation. But in reality, if the radiation source is, say, packaged or shielded in a way that this, so is it possible that this law is not obeyed, and how would that affect like the resulting optimization? Yeah.
So the results still hold through, and the whole formulation carries. I'll show you exactly where the change needs to happen. Okay, so give me a moment to bring up the right slide. Okay. Okay, going back here, nothing really changes in the case that you have a shielded source, as long as you have some information about the amount of shielding. Because basically what happens is that this product here of chi and A and chi, so these are the two parameters that you might have to adjust in the whole formulation. So as it turns out, when you shield a source of radiation, basically you change the effective activity of the source. So it's as if you're having a lower activity source instead of the original one. So instead of having your original A, you would have an A prime, which is an order of magnitude smaller depending on the amount of shielding that you have included.
That makes sense.
So you can, this is the best way to include that in the formulation, but you can also you may have to adjust. That depends on the experiment, and we have done this type of experiments ourselves, because in the process of time, the radiation source that we had was decaying and was changing in radioactivity. So in the process of calibration, sensor calibration, we had to make small adjustments on the chi, which had to do with our sensors, and the alpha that we were using in our experiments. But as long as you fit these parameters here in the right way, everything else follows through.
I guess I have a slightly follow-up question to that. That seems to assume that radiation source is evenly shielded in all directions. But I guess if you had a radiation source that was unevenly shielded, so there was like one, I don't know, dense material on one side and not on the other, then
Yep.
you would have a spatial component to how that would affect your search, in addition to just the distance and certainty.
Mhm.
Do you have a way for adapting to that, or is that its future work?
Sorry, you were breaking up a little bit towards the end.
Sorry, I was asking if you have a uneven shielding that would probably affect the formation that the drone should fly in, because you have to find where the shielding is weakest to best detect the source. Can you speak to that at all?
Yes, definitely. And I will push your question even a little further, saying that there's another way that you can tweak the problem and create a little bit of trouble here by assuming even sensor non-homogeneity in terms of directions. So sensors that are not uniformly picking with the same sensitivity in all directions. So these are valid questions. To be honest, this is where I would look to try to make changes. It's not clear to me how you would address right on top of my head this type of non-homogeneity in terms of directional heterogeneity. It will definitely affect the outcome of the optimization once you take into account this type of difference in terms of direction. So it would give you, the optimization is bound to give you solutions that are biased towards approaching the sensor from a particular direction where the shielding is lower. But I would stay short of saying that I would use the same structure of equations that I showed you today in the case of non-homogeneous emission and shielding. So the short answer is yes, it definitely impacts the solution. With knowledge of the shielding geometry, you can probably do something. I don't have a direct answer right now as to how the equations would look like or how the solution would look like.
Okay, thank you.
Did you ever look at multiple sources?
Oh, very good question. Short answer, no. The funding for this effort kind of dried up. So there was only a certain point towards which we could push down this direction. It was definitely one of these follow-up topics that we could pick up. My hunch is that you would end up with a solution that would split your formation in different clusters, so that you could chase. You would have to do some target assignment and you know, the network decomposition to go after a scenario like this. But in the context of what I've shown you today and what we have done so far, we haven't included the possibility of multiple targets.
Yeah, maybe
I don't see.
Yeah, maybe it's part of the co-design of a fourth target assignment portion.
Yeah, I mean, most of the weight for the co-design to adapt to a case of multiple targets would go on the motion control, you know, the sensor deployment. The other components would stay pretty much the same, just copied, right? And on the different clusters that you might have, you have to split your network in order to chase down the different targets.
Yeah.
But you might have to put some thought on how to do the splitting between how to assign robots to different targets and go after them. Yeah.
Yeah, definitely an active area of research.
Yep, I agree.
I think that's about it. Does anyone online have any questions? We'd like to thank you for coming to present and hope to hear more from you in the future.
Thank you so much, Chris. Thank you for the opportunity. And thank you all for your attention.